For more problems and videos like this for linear algebra, you can take a look at Sarai Studies, link is in the description box below.
In the last video, I showed you how to go from the generating set of the column, row, and null space of your matrix A to a basis. Now, sometimes they'll give you a set. They won't say that it's a generating set. They'll just give you a set of vectors in some dimensional space, and they'll ask you, is it a basis? Now, the main rule for a set of vectors to be a basis of some dimensional space is that when you put it into a matrix, all of its rows and columns will have pivots. Pivots are your leading entries in row echelon form, so that means to tell you that you actually have to get it into row echelon form. And if all of the rows and columns have pivots, then yes, it's a basis. So you can do that for all of these that you're going to see. But there are some tips and tricks that you can use by looking at it and determine if it's a basis or not. So the first tip is to use the number that they give you right here. If they're asking you if this set in this three-dimensional space of all real numbers is a basis for R3, then in order for it to be a basis, it has to have exactly 3 vectors, 3 columns in that set, and it doesn't. So automatically we can disqualify this from being a basis of R3 and not even bother to check this condition because we know that it just can't be. So that's the tip. If you're given any dimensional space M of all real numbers, so M could be 2, it could be 3, it could be 4, whatever, then B, your basis, should have M amount of columns. So if this is M, then any basis for R of M or R of 3 should have 1, 2, 3 vectors, and this one has 2, so automatically we can disqualify this from even being a basis of R3. Now, what if it said R2? Then yes, we have 2 vectors, but that doesn't necessarily mean it's a basis. You still have to check this condition, put it into row echelon form, and make sure that all of the rows and columns have pivots. We use this tip more to disqualify sets as being basis and save us time. At the end of the day, no matter what we do, we still have to check this condition to prove that it is a basis. So no, this is not a basis of R3 because I see only 2 vectors instead of 3. So again, it's just a set of vectors in this 3-dimensional space. The first thing I do is I kind of try to disqualify it. I see, okay, it's asking if it's a basis of R3. We have 3 vectors. Okay, fine. But it doesn't mean that it's a basis of R3. It just means that it has a chance. So we have to check if all of the rows and columns have pivots. These are just your rows and columns in your matrix. This is already in row echelon form because you see your diagonal, all your zeros below your leading entries. Because it's in row echelon form, our pivots are leading entries. And so we can see already every row has a pivot. Every column has a pivot. So it satisfies this condition. So yes, this is a basis of R3. Here's another tip and trick. Here you have this set. If you see the 0 vector, a 0 column, you already know it cannot be a basis of R3 because basis is made up of independent vectors. Vectors that are not redundant, that can't be replicated with another vector in that same space. The 0 vector, you can literally take any 2 vectors, let's say this was R2, it doesn't matter if it's R3, R4, whatever. In whatever dimensional space, you can take any 2 vectors and combine them to get the 0 vector. So the 0 vector is not independent. It depends on other vectors. You can create it with other vectors. And so because I see the 0 vector in this set, I can automatically disqualify this set as being a basis for R3. So that's this other rule here. If a vector is a 0 vector, then not a basis. This is a set of vectors that they give you. They're telling you that it's in this 3-dimensional space of all real numbers. Is it a basis? Well, you can use this rule. If it's a basis of R3, then it should only have 3 vectors, 3 columns. I see 1, 2, 3, 4. So automatically I can disqualify this from being a basis, and I don't even have to bother checking this condition because I just know it's not a basis. It's supposed to only have 3. No more, no less. So no, because I see 4 vectors, it's too many, it only needs 3. Now, we answered the question of whether these sets are bases of R3, but there's another question they can ask you. If it's not a basis of R3, then how can you make it a basis of R3? So I know that we proved that this was not a basis because of this condition, but if I put all of my columns in a matrix, and then you get it into reduced row echelon form, and I already recorded a video on how to get into reduced row echelon form, it will be linked under Sarai Studies under this video, or if you scroll all the way to the end of the video, it should pop up on the right side in the last 20 seconds. But the idea is, we disqualified this from even being a basis because there were 4 vectors instead of 3, so there were too many vectors. But we could have just checked the basic condition that when you put this matrix in echelon form, reduced row echelon form, you'll be able to see the pivots, which are just your leading entries in row echelon form. And you'll see that every row has a pivot, but not all columns have pivots. This last one does not have a pivot, only these columns do. And so it just automatically did not satisfy this condition either, but we kind of saved time by using this condition. So if the issue is that there were too many vectors, then maybe the solution is to take away a vector, but then the question becomes, how do we know which vector to take away? Is it this one? Is it this one? Long story short, you take away the one that doesn't have a pivot. So this has a pivot, this has a pivot, this one does, but this one does not. Because remember that your basis is just made up of only independent vectors. Independent vectors are the ones that are pivot columns. Each has a pivot. So you don't want any dependent vectors in your basis, so you remove this one. This is called a reduction theorem, where you're removing a vector, you're reducing the set until you get a set where you can check the condition again and see if it satisfies it. In other words, until it becomes a basis. So if I were to give you this one, just like I gave you these, and ask you if it's a basis, well, first of all, you would check that there's just enough vectors. There's 3, good. So it has a chance, but you still have to check this condition. So then you would put it into a matrix form, which literally would just be this, right? It's the same thing, but without this vector. And then you would row reduce it, which would literally just be this. So same thing, but without this vector. And then, is it true that all of the rows and columns have pivots? Yes. Every row has a pivot. Every column has a pivot. And because of that, we can say that, yes, this is a basis. So we just kept removing vectors from the original set until we had linearly independent vectors, and also this condition was satisfied. And then we can say that, yes, this is a basis because it passes this condition where all of the rows and columns have pivots. Now let's move on to this one. The problem here was that we had a 0 vector. So if we were just to remove that for a second and look at this one, pretend that this is one of the sets that I gave you, ask yourself, is it a basis of R3? You would say no, because there's 2 little vectors. Here we have 1, 2 vectors when we're supposed to have 3. So here the problem was that there were too many vectors. Now here the problem is that there's 2 little vectors. So when there were too many, we took away a vector until we got what we wanted. So how about we just do the same? There's 2 little, so how about we just add a vector until we get what we want? Now, which vector should we add? Well, obviously you're not going to choose a vector like 2, 0, because this is a vector in the second dimensional space of all real numbers, right? In just your coordinate plane, just a point. That's not even in the same vector space. So it's not even in the same world, that vector. You want to choose a vector that has 3 entries. That's in the third dimensional space of all real numbers. So in this little world right here. And it's up to you which vector you choose. You can literally choose anything, but at the end of the day, the way that you check if the vector that you chose was the correct one is by putting it into matrix, row reducing it, and checking if it has pivots in every row and column. So I'm going to move it over here, and let's say that I want to add maybe this vector 0, 0, 1. It's just a guess. So to check that we're right in picking this vector, what does it mean for us to be right? Well, if we get what we want, if this is a basis. What does it mean for it to be a basis? If when I row reduce it, all my rows and columns have pivots. So I'll actually go through this row reduction with you. You want to start with your leftmost non-zero column, that's this one. Your pivot position is at the top. Your job is to kill everything below that pivot position and make it 0. So I want to kill this one, which is in row 3. So I want to kill something that is in row 3, and I want to use whatever's inside my pivot position to do so. My pivot is in row 1. And then my equation becomes plus, and then whatever's here, which is row 3. And then to find what I need to do to manipulate this equation so that this becomes 0, I'm going to write these rows down here. Then I ask myself, what's my goal? My goal is for this entry to be 0. That's the first entry in a row. Then I focus on this column, and I ask myself, what can I do so that this plus this gives me 0? Well, this would have to be a -1. How do I get it to be a -1? By multiplying by -1. But whatever I do to one entry, I have to do to the rest of the entries in that row. So I'm going to take that entire row, multiply by -1. So this becomes -1, and these are insignificant. Then I get what I want. 1 minus 1, 0, just like I wanted. This is 0, this is 1, and this is my new row 3. So now my row 3 becomes this. This is still my pivot position, and everything below it is 0, so I'm done with that. So I cross out the row and column, and then I focus on the submatrix formed when I did that, which is this. And you repeat the steps. You start with your leftmost non-zero column, that's this one. Your pivot position is at the top. Your job is to kill everything below that pivot, make sure it's 0. It is already. So I'm already done with this one as well. Then you focus on the remaining submatrix again. Leftmost non-zero column, I mean, this is the only column here, not really much of a column. Pivot position's at the top, and then your goal is to kill everything below it, make it 0, but there's nothing below it, so you're also done. So this is already in row echelon form, and you just need to get to row echelon form to find if there's pivots or not, and you can see that every row has a pivot and every column has a pivot. So we made the right choice in choosing this vector, because it satisfies the condition of a basis that all rows and columns of the matrix A, when reduced, has pivots. So we can say that this is a basis of R3. Now this is called the extension theorem because we extended our set by adding a new vector until we got what we wanted, a basis, which is the opposite of the reduction theorem where we reduced our set by removing a vector until we got what we wanted, which was a basis. Now let's move on to this one. This is already a basis, so it's unapplicable. And then over here, the problem was that there were not enough vectors. There were too little vectors. Just like over here, there were 2 little vectors, so what did? We added a vector until we got what we wanted. So the question is, what vector are we going to add? Well, you can add any vector. So maybe I'll try 4, 5, 6, right? As long as the vector has 3 entries, it matches these, it's not in a whole other world, then you can add it. And you can check if you were right by adding that vector. By doing what? Well, you ask yourself, well, what is the situation when I'm right? Well, when I put these columns in a matrix, I get into row echelon form. And if all the rows and all the columns have pivots, then I'm right. So in other words, just do exactly that. So again, get these columns in a matrix and you get it into row echelon form. I just got it to reduce row echelon form for the sake of it. I did record a video on how to do this, so you can either check it out at Sarai Studies or you can just scroll at the end of the video and this video should pop up on the left. The idea is that a pivot, remember, is just your leading entry in row echelon form, reduced row echelon form. So it's this one, and this one, right? Because these are your first numbers that you see that are not zeros in each row. And so essentially you have a pivot in each row and you also have a pivot in each column. So it satisfies the conditions of a basis that you take a matrix A and when you row reduce it, you have pivots in each column and in each row. Beautiful. So you were right in choosing this vector. Again, we use the extension theorem where we just kept adding a vector. Now note, you could have added any other vector. It didn't have to be these, which should tell you that, hey, bases are not unique. You could have had another vector right here and it still would have been a basis for R3. So keep that in mind, and that's it for this video. You should now be seeing on the left side of the screen the row reduction for this matrix A, and on the right side of the screen the row reduction for this matrix. Alright, I'll see you in the next video.